Let's say two teams go for a race. Team Red and Team Blue. Team Red decides to go straight up the hill. And Team Blue decides to roll themselves up to the top of the hill. Question is, which team did more work? Team Red or Team Blue? And the answer might surprise you. In fact, they've both done the same amount of work. It doesn't matter if you decide to lift an object from point A to point B, or if you decide to push an object up a frictionless ramp from point A to point B. Both scenarios require the same amount of effort and the same amount of work. How about this scenario now? I know the picture looks rather weird, but just trust me, they both start at the same elevation at the bottom of the hill, and they both finish off at the same elevation at the top of the hill. You guys ready? On your marks, get set, go! Woo! Hooray! They've both done the same amount of work, have they not? But clearly there's something different. You might have noticed that Team Red probably put in the same amount of work, but in a shorter amount of time. As a result, Team Red is probably sweating like crazy. And that's because Team Red has produced something known as power. More power compared to Team Blue. By definition, power is the rate that work is being done. Power is measured in watts, in honor of James Watt. So power is rated as a joule per second, which is not a fundamental unit, it's a derived unit, and a watt is also a derived unit. Let's break this down. We know that a joule is equal to force times distance over time. Well, force is measured in kilograms times meters per second squared. Distance is measured in meters, and time is measured in seconds. If you try simplifying this down, you get kilograms times meters squared over seconds cubed. These are the fun and exciting fundamental units of power measured in watts. And now you know. Another way of writing out the power formula is that you can replace work with change in energy. So power is the rate that the change in energy happens over time. Here's an example. What's the power of a person pushing a box 6.4 meters at a constant force of 525 newtons in 5 seconds? We know that work is equal to force times distance, so we may want to calculate that out first. And power is equal to work divided by time. So then we take that answer and we divide it by 5 seconds. Or you could just simply sub one equation into the next and come out with a bigger equation like this one here. That way you can directly sub all the values in and get to an answer of roughly 600 watts, which is quite a bit. Just in comparison, if you didn't know any better, this is slightly less than 1 horsepower. By definition, a horsepower is equal to 745 watts. There's the conversion ratio. All right. So if you want to take the time to try converting it right now, go ahead. What is the equivalent amount of power in horsepower? Hope you got less than 1. And there you go. And horsepower, yes, should be written in lowercase, lower p. That's the SI correct way of stating it. Speaking of horsepower, maybe you want to know more about it. Where did that crazy term come from? It has to do with the fact that James Watt, he was analyzing the amount of power that a horse can produce. And usually horses were used in these milling stacks where there would be a grinder, and then you place the hay into the grinder, like so. Sorry about my terrible picture. So the horse will be walking around in circles, grinding all of the wheat, turning it into flour. Now, a horse can apply a certain amount of force non-stop all day without getting tired. It's kind of like if you're a fit student. You should be able to walk pretty much non-stop for at least half a day without getting tired. I remember doing that when I was your age. All right. But horses, they're a lot stronger than us. In fact, a horse can equivalently lift a person up off the top of a hill at a comfortable walking pace and never get tired of it. All right. That's how strong horses are. And they pace these horses such that it takes them about, a minute to go around twice? A minute to go around, 2.5 times. Okay, 2.4 times 2 pi. So they can walk around this loop 2.5 times. The radius of the loop is 12 feet. And they're able to accomplish this non-stop. It works out to this numerical value over here, right? 33,000 foot-pounds per minute, which is the equivalent of 1 horsepower. There are other geeks out there that did interesting things as well, such as the Magdeburg hemisphere. Not sure if you've ever seen them before, but these are hemispheres where they remove all the air from the inside. And these are pretty big. They're about the size of that, about 30 centimeters. All right. And on each end of them, it was connected to 15 horses. I wouldn't use horsepower as a proper definitive definition, but they had about 30 horses and they couldn't rip it apart. And that was just to prove that we have about 300 kilometers of air squishing down on these two hemispheres. And with that 300 kilometers of air, it provides so much pressure that not even 30 horses can rip it apart. Pretty neat experiment. Thanks, Mayor. Here's another problem. What is the power of a person lifting a 100 kilogram box up 2.2 meter stairs in height in 5 seconds? That's intense. 100 kilograms is not light at all. That's 220 pounds. All right, so let's start off with what we know so far. We know these values here. This time around, we notice that the work has to do with lifting an object. So the work involved is now mg delta h. And for power, we divide work over time. So the formula for power lifting an object up is mgh delta t. We sub the values in and crunch it out. And in this case over here, this person is pretty jacked. Still less than horsepower, but that's still a lot of effort. Well, let's think about this now. Instead of 5 seconds to do the job, let's say it takes them 10 seconds to do the job. What will happen to their work? Good, it remains the same. What about the power? Well, it took them twice as long, so the power would cut down in half. So it would be somewhere in the realms of 2.2 or 220. 215, I suppose. 215 watts. And is less work done if the box was rolled up a frictionless ramp? Remember at the beginning of the video, it won't make a difference. All right. And that's why, for example, if you're trying to move a piano up to the back of a truck, you probably wouldn't try just lifting it straight up and putting it to the back. Instead, you would try to push it up a ramp, hoping that there are some decent wheels at the bottom of the piano so that you're not putting in too much effort. Because what's really happening is that you're spreading out the force over a greater distance. So your work is the same. So even though your force is decreased, your distance is increased, and those two balance out to the same quantity of work. Mechanical advantage, if you remember that. Next topic of today is on efficiency. And efficiency by definition is the energy out divided by the energy in. And yes, you could divide that by time, which would be equivalent to power out divided by power in. Let's go through this example. A poor bat swing delivers only 10% of its kinetic energy to a 100-gram ball. How fast will it move now? All right, let's work through this slowly. Now, I think intuitively, you guys would probably already know the answer for this. 10% of 40 is equal to 4 joules. But let's show all of our work. How would we do that? We start off with the formula efficiency is equal to E out divided by E in times 100%. We'll bring the E in all the way up here. So we have E in times percentage efficiency, and we divide both sides by 100%. And that's why it'll look like the formula in the middle. We then sub everything in carefully, and lo and behold, you get the same answer, but at least we've shown our work. Next, we're going to transfer this energy into motion. So since EK is equal to 1/2 mv squared, then your final speed is equal to 2EK over m square rooted. Right? So the energy out results in a change in kinetic energy. However, it will be our EKF. Why? Because we're taking it that the that the ball was stationary upon contact, so that goes to 0, and now it contains this much kinetic energy. We then sub the values in. Don't forget to convert your mass properly now. That's 0.100 kilograms. Crunch it through, and the square root of 800, I can't do it on the top of my head, gives you that. Or square root of 80 gives you that. Okay, 8.9 meters per second. And if you decide to multiply that by 3.6, you'll get it in kilometers per hour. And, you know, in sports, often is measured in miles per hour for baseball. So if you're curious, it's a 20 mile per hour ball afterwards. Not very fast at all. For more adventures like this, get started on your homework. How about now? Sure. A 65 kilogram student climbs 5 meters up a rope in gym class at a constant speed of 1.4 meters per second. Determine the time it takes for the student to climb up the rope and then determine the student's power. So, for A, the time it takes, well, we're probably going to do distance is equal to speed times time. So time is equal to the vertical distance divided by the vertical speed. So the student's able to climb 5.0 meters up at a rate of 1.4 meters per second. Pull out our handy dandy calculator. 5 divided by 1.4 gives you 3.571 seconds. All right. And then determine the student's power. Power is equal to mg delta h over delta t. So it's a 65 kilogram student times 9.81 newtons per kilogram times the height of 5.0 meters divided by a time of 3.571 seconds. $893 watts. All right. Determine the student's power without finding the time. And some of you guys might be stuck on that part, and that's why you're watching this video here. All right, how would you solve it without finding the time first? Well, this formula over here, it can be written in a different way, yet still bear the same meaning. For example, I could write it out like this. Is it still not the same formula? Right? It's m times g times h divided by t. It doesn't have to divide all of them by t. It just has to divide by t. It's kind of like how surface area is equal to either half base times height, or you could also write it out as surface area is equal to base times height divided by 2. They both bear the same meaning. But in this version over here, what is the definition of height over time? Exactly, Vy. So 65 kilograms times 9.81 newtons per kilogram times a Vy of 1.4 meters per second. Now we avoided calculating out time. So 65 times 9.81 times 1.4 will give you the same exact answer, 893 watts. Units always have to work out. Several students in an auto shop class need to lift an engine out of a car using a rope and pulley system. The mass of the engine is 170 kilograms. By pulling as a team, the students can exert a force of about 1,720 newtons to lift the engine to the necessary height of 2.2 meters to work on it. How much useful work was done by the students? So I think it's the most efficient amount of work that was done in lifting it up. So not worrying about friction or anything, the most amount of useful work is just on lifting up the object as is. So the work is equal to mg delta h, just lifting it against gravity. So it's a 170 kilogram engine. They're doing this here on Earth, and they're lifting it up to 2.20 meters, which is pretty high. And we get 3669, I believe. Yeah, 3669 joules of work. How much work was done in total to lift the engine? And we're talking about the work due to the pulley. all right, and physically pulling it up. And that would be equal to force times distance. The boys were pulling with a force of 1720 newtons, and they're pulling it up a distance of 2.20 meters. All right, so there was probably the engine itself connected to a hoist, up some sort of pulley, and the kids tried pulling at it. All right, so that's the work that they were doing in trying to pull it, as opposed to the amount of effort in really just fighting against mg. All right, so due to any sort of friction that may occur in the system, that probably is the reason why this value over here will be greater. So 1720 times 2.2 gives you 3784 joules. So you can see the value has increased. As for the percentage efficiency, that's equal to work out versus work in. So in this case over here, the amount of useful work was 3669 joules, and the amount of work that they really put into this is 3784 joules multiplied by 100%. After all, if the two values were the same, then they were at 100% efficiency. All right, but because there was less useful work done than the amount of effort put in, they're less than 100% efficiency. So 3669 divided by 3784 multiplied by 100 just to convert it into a percentage, and we have a 97% efficiency. There you go. A 50-kilogram student jogging at 5 meters per second in an IKEA parking lot is suddenly being chased by a crazy little monkey. If the student outputs 500 watts of power over 2 seconds while accelerating, what is the student's final speed? All right, so we know that work is equal to the change in energy, kinetic energy more specifically. We also know that work is equal to power times time, or power is equal to work over time. That way we can write down power times time is equal to 1/2 mvf minus 1/2 mvi squared for our change in kinetic energy. We're just looking for our final speed over here, so the preference is up to you. If you feel more comfortable subbing in the values and rearranging, by all means, or if you want to learn the art of rearranging, well, let's do that together. So we have 1/2 mvf squared is equal to p delta t plus 1/2 mvi squared when you bring it over to the other side. Now we need to multiply everything by 2 and divide everything by m and square root it. So vf is equal to the square root of 2 p delta t plus 1/2 mvi squared divided by m. And we have a final speed of 8.06 meters per second. So the person started off at 5 meters per second. After putting in about 1,000 watts of power, they gradually increased up to 8.06 meters per second. Excellent. In a race, a 54-kilogram athlete runs from rest to a speed of 11 meters per second on a flat surface. The athlete's body has an efficiency of 85% during the run. How much input energy did the athlete provide? All right, so work is equal to change in kinetic energy. So 1/2 mvf squared minus 1/2 mvi squared, but starts from rest, so this term goes to 0. Now you can figure out how much useful work the student has put in. So 1/2 of 54 kilograms times the final speed of 11 meters per second squared gives you 3267 joules. But the body is only 85% efficient. So this is the useful output work. So percentage efficiency is equal to out divided by in. And the question is, how much work input did we place? That's equal to the output divided by the percentage efficiency. So 3267 joules divided by 0.85 means that this number should grow. So we'll take that divided by 0.85 and we get 3844 of input energy. Done. A golf club with 65 joules kinetic energy strikes a stationary golf ball with a mass of 46 grams. The energy transfer is only 20% efficient. Calculate the initial speed of the golf ball after it's been striked. So it probably is the final speed after the fact, because the initial speed was at rest. Okay, so first thing we need to figure out is 20% of 65 joules, because we're looking for E out. E out would be equal to E in times percentage efficiency divided by 100% if you're able to rearrange that in your head. I know that for most of you, you guys will just type in 65 times 0.2 and it will yield the same answer. But when you are asked to show all your work, this is how you show all your work. And this is how you do it on your calculator. So only 13 joules makes it into accelerating the ball. EK is equal to 1/2 mv squared, so the final speed is equal to the square root of 2ek over m. So 2 times 13 joules kinetic energy that has been transferred to it, divided by 0.046 kilograms. And there you have it. An athlete who competes in downhill skiing tried to lose as little energy as possible. A skier starts from rest at the top of the hill and skis to the bottom as fast as possible. When she arrives at the bottom, she has a speed of 23 meters per second, as opposed to 35.7 meters per second under super efficient terms. So calculate out the efficiency of the skier. So we are going to look at the theoretical maximum speed if there wasn't any friction involved. All right, the skier starts from rest, so you know their 1/2 mvi is at 0. When she arrives at the bottom, mg delta f goes to 0. So let's figure out what the theoretical maximum speed it is at the bottom. We'll also notice, just like before, since every term has mass, you could technically just divide that out because it won't matter anymore. As long as you don't have to worry about friction, Vf is equal to 2g delta h rooted. Times the height of elevation of what? 65 meters tall. So it doesn't matter if it has a gradual slope or if it has a steep slope. By the time the skier gets down to the bottom of the hill, as long as they have the most efficient skis in the world, they will both travel at the same exact speed at the bottom. The only difference is that this guy will make it to their final speed at a sooner time. All right, they will accelerate far greater and then reach that final speed far sooner. That's the only difference. Otherwise, the speed on both of them will be exactly the same in both scenarios. Conservation of energy. So root of 2 times 9.81 times 65 gives you 35.71 meters per second hypothetical maximum speed. All right. However, you may notice that the actual measured one is 23. You might be tempted to divide 23 by 35, hoping for the correct answer, but that won't work out. And that has to do with the fact that when you take a look at kinetic energy, it's not linearly proportionate to speed. Instead, it's a quadratic correlation. So when you're trying to solve for these type of problems for percentage efficiency, you have no choice but to do 1/2 mv out squared divided by 1/2 mv in squared to find out the true value. After all, you're trying to figure out the right-hand side of this equation, how much energy you had when you're at the bottom of the hill. So yeah, we're kind of doing some extra steps over here that are unnecessary. We probably could have just had that right over down here, and that would have worked out. Anyways, looking at this, we may notice that we don't really need to worry about the 1/2 or the mass. We're just looking at the V out versus the V in, and you can square it after the fact if you wanted to. All right. So her actual attainable speed was 23 meters per second, and theoretically it should have been 35.71 meters per second. Once again, you couldn't just divide that to get to the answer, and that's because the energy is quadratic in relation to the speed. So in other words, it takes you more effort to get to a faster speed. If you do the math for it, by the time you double your energy, your speed has only increased by about 41%. It has not doubled. How do I know that? What's the square root of 2? All right, so open brackets, 23 divided by 35.71, close bracket, squared, 42%. Explain why the mass of the skier is not required in calculating the efficiency. You'll notice that it will just divide itself through, and that's why it doesn't matter. Okay, because we're comparing between the same objects before and after. The skier could have had double the mass, and the percentage efficiency would be the same. Remember, it doesn't matter if you drop a crumpled up piece of paper and a rock at the same time. As long as you don't worry about air friction, they will both accelerate at the same rate, and they will have the same final speed at the bottom. All right, so this one over here, the challenge comes from, yet again, this formula. Power is equal to mg delta h over delta t. How do we associate these two together? One part of the problem, it says this weird thing here. The water is pumped at 1.48 kilograms per second. That is literally measurement of mass over time. Take a look at the units. So really, we're just taking this formula over here, and we just have to do a small rearranging for it, which again, mathematically, these two equations are the same, but they visually look different, but to our advantage, because m delta t is equal to 1.48 kilograms per second, multiplied by 9.81 newtons per kilogram, multiplied by a height of 37.0 meters. So then you'll get the kilograms dividing each other out, and you'll get newtons times meters over seconds, which is the same meaning as a watt. So 537 watts of useful output. Now, this pump put in 750 watts, but only 537 was attributed into pumping the water. So your percentage efficiency is equal to power out versus power in. So the useful output was 537 watts, but 750 watts was placed into the motor itself. If you've ever felt motors before, they aren't 100% efficient. They do get rather warm, so make sure you cool it properly. 71.6% efficiency, and yeah, 3 sig fig, let it be. There you go. All done. Catch you later.